This is a video for example 10.5.5 in Greenberg's book, talking about mass balance in chemical reactions and thinking about that as an application of the ideas of rank and linear independence that we've been talking about. So in a chemical reaction, you have reactants and products. So for instance, in equation 10.5.5 for A, B, and C and D, Greenberg talks about some various chemical reactions. So there are four reactions we're talking about here. So the first reaction is that carbon monoxide plus half of an oxygen molecule is converted into one CO2 molecule. Obviously you can't have half an oxygen molecule, so this is effectively more like two carbon monoxide molecules plus one oxygen molecule is converted into a pair of CO2 molecules. That's one reaction. Another reaction is where we have a single hydrogen molecule plus a half of an oxygen molecule goes to a water molecule. Another reaction is that we have a methane plus 3/2 of an oxygen going to carbon monoxide plus 2 waters. And the last reaction is that we have a methane plus 2 oxygens goes to CO2 plus 2H2. Oh, so in chemistry, the rules of mass balance say that when 1 unit of this reaction proceeds, you have to eat up everything on the left in proportion to the amount that you produce on the right. Now the question is whether these reactions, as we have them listed, these mass balance conditions, are independent of each other, or if maybe one of them can be expressed as some combination, some linear combination of the other three. So in other words, if I have some smaller subset of these reactions, do they actually imply the balance of another one, or at least can they be can the last condition be thought of as a combination of the others? So I can think about this mass balance. So if I write this in terms of an equation, I can think about it as a matrix A, which represents the coefficients in the mass balance, and each column will correspond to the given molecule. So for instance, I can have a column corresponding to carbon monoxide, a column corresponding to oxygen, a column corresponding to carbon dioxide, a column corresponding to hydrogen, a column corresponding to water, and a column corresponding to methane. Okay, and each reaction gets a line as an equation, and the first mass balance equation tells me that 1 unit of carbon monoxide, so the first reaction involves, so my first reaction involves carbon monoxide, oxygen, and CO2. So carbon monoxide and oxygen are reactants and CO2 is a product. So I can write that balance as 1 unit of carbon monoxide plus half a unit of oxygen has to equal, so this is on the other side of the equation, become 1 unit of carbon dioxide. And so I can look at the second reaction, and so the hydrogen is going to come in with none of the other molecules participate in the first reaction. In the second reaction, the hydrogen and oxygen are going to come in with plus signs. So here's my hydrogen, I get a +1. My oxygen, I get a +1/2. And then the water is a product, so it gets a -1. None of the other guys participate. In the next reaction, I have methane and oxygen become carbon monoxide and water, and no carbon dioxide or hydrogen in that reaction. And then finally, I have methane and oxygen becoming carbon dioxide and water with no hydrogen or carbon monoxide. Okay, so we would like to try to understand if this set of 4 mass balance conditions is independent, or is one of them possibly a combination of the others. So we have 4 equations and 6 unknowns, so the rank of this matrix could be at most 4, but let's go ahead, we will do row reduction. So if I go to Wolfram, there we go, and I enter the mass balance matrix, so I've got 1, 1/2, -1, 0, 0, 0. That's my first reaction. My second reaction, let me enlarge this so you guys can see in the video better. My second reaction, that's a 0, 1/2, 0, 1, -1, 0. My third reaction, it's a -1, 3/2, 0, 0, -2, and 1. And then my last reaction is 0, 2, -1, 0, -2, 1. So when I do row reduce, the question is whether or not I have 3 leading ones or fewer. And lo and behold, in my row reduced form, I only have 3 leading ones. I could have had 4, but apparently one of those equations is implied by the other 3. I can always write 1 as linear combination of the other 3, which means that there are really only 3 independent conditions rather than 4 independent conditions. So we can write the row reduced matrix. Well, so let's just say that the rank of A is equal to 3. So this is equivalent to saying that there are only 3 leading ones as opposed to 4 leading ones. This means that one condition is redundant or implied by the other 3. So it would be possible to write a reduced set of mass balance conditions, 3 reduced mass balance conditions that actually imply all these conditions here. Okay, so in other words, this specification has some redundancy in it, and that's equivalent to saying that the rank is 3. Notice that 3 is less than 4, which would have been the full rank condition. So this is one example of where the concept of rank and the number of leading ones is important in an application.